here we are. We've arrived at one of the more seminal challenges defining 21st century geometry, and that is the intersecting points of two overlapping circles. And what makes this 21st century is that it's hard to imagine anyone being able to solve this in any general sense without the automated arithmetic, the high-level delegation of transforms that have to be computed, and the thinking tools using direction vectors in place of angles. It's hard to imagine being able to tackle this without those technologies of practice and thought. So this will be an exciting watershed when you have it solved, thinking that you'll be in quite an elite class of problem solvers who now understand how this works. And you'll be amazed at the number of applications that open up once you have this basic advanced algorithm in 2D geometry. So let's dive into the sketching part of the problem, and I'll guide you through the part of it I think you might need a little help with, and you'll tackle all the rest of it. The intersection points of two overlapping circles, C1, C2, when you get this solved, you'll have stepped up to a whole new level in geometry. Very few people know how to do this, but you already have a great foundation in problem simplification that you're going to put to work on this. And I'm going to hand that transform part of it over to you 100%. And all I'd want you to do to get ready to solve this is to get sketching and sketch your way into this special case, and I'll help you with the algebra to solve the special case, and you'll take it from there to the finish line with back transforming your intersection points. Let's take a look at the special case, and I'm marking everything as in doubly transformed coordinates. You're going to take care of getting it there and getting the results back. Okay, so we've got our two circles, C1 double prime, C2 double prime, and they're in this configuration, and got our two intersection points. So we're going to need to do some algebra. And so we're going to need some variables. So the first one, we're going to call the distance between the centers C. And it'll be the same distance as they were in the original coordinates. So this is easy to compute. And the thing we need to solve for is the coordinates of I1. And so we're going to need the result for A, the distance from the origin out to the x-coordinate of the intersection point. We're calling that x-coordinate A. And then we're going to call B the remainder of the distance out to the center of C2 double prime. Okay, and the goal is going to be to solve for A because we want this x-coordinate. And so let's write this down so we know by choice we've made A plus B equals C. Okay, so now what we're going to need to solve this are two right triangles. So these are the two right triangles we're going to need. And so let's mark in everything we know about them. So we have R1 and R2. They're going to be given. And we've got H, the height. It's going to be the y coordinate of I double prime. That'll be unknown and has to be solved. Okay, so let's write down our givens for this special case. So our givens will be that intercircle distance, C, the radii for the two circles. And what we're trying to solve for here are the coordinates of I1 double prime. And those coordinates will be A and H. So this is what we want to focus our algebra on, is getting A and H. Okay, well, let's use our right triangle, first right triangle, the gold one. And so we have a Pythagoras equation. So A squared plus H squared equals R1 squared. Everybody see that? So that's for this right triangle. And then we've got the red right triangle. We've got also B squared plus H squared equals R2 squared. Okay? Everybody with me? So the first step we're going to do is eliminate H squared. So just subtract the second equation from the first. Now I've got an A squared minus B squared on the left. And I got an R1 squared minus R2 squared on the right. Okay, so the next thing I'm going to recognize is I've got a difference of squares, and I can factor it. So you remember this, right? So A plus B times A minus B is the way you can factor this difference. And the reason why that buys me something is I can substitute for A plus B. I got A plus B equals C by construction. And so now I have a C times quantity A minus B on the left side. Now I can divide both sides by C. So now I just have my difference A minus B. And over on the right, what I had before now divided by C. And can anybody see the way now to move forward? I've got the difference A minus B on the left side. Do you remember how to solve if you have the sum and difference of two variables? So we have A plus B. And so now we've got the difference and the sum of two variables. You solve this by just adding the two equations. That gets the B to drop out. And we get 2A on the left side. And now we've got what we had before on the right plus a C. That came from here, adding this. We're almost there. So what I'm going to do is now put everything on the right side under a common denominator, C, so that means this term C over here becomes a C squared over C. I move it inside the parentheses, put this under a common denominator, and we have an answer for A. So we'll just divide both sides by 2, and looks good. We've got, this is a given, R1, R2 is a given, C is a given, C is a given. So we've got our unknown A now be calculable in terms of all givens. Boom. That's nice. Okay, so once we have this solved for where the x coordinate, we can just use our right triangle solver to get H. And so you've got two different choices. H can either be right triangle solver R1 comma A, right? Hypotenuse leg, or it could be right triangle solver R2B. But we don't have B. We never solved for B. So I guess we'll go with this one. So there it is. You have A, you have H. Both, you got to calculate A first. Once you get A, you can calculate H. And once you get both of those, you can calculate I1 double prime. We're assuming you can then calculate I2 double prime. And you're on your way back home. Before we leave this treatment and I send you back to work out the general case in your sketch, there's just one refinement we need to make here to deepen our understanding of what the results might look like. So it turns out over here for A, it's not necessarily A is going to be positive. It's a coordinate value, as is B. So you want to indicate on your sketch that A and B are coordinates. They can range positive or negative. So for instance, if C2 were greatly enlarged and brought way over here, so it is possible to have intersection points way over here, in which case the A coordinate will be negative. And you can see that in this formula because of the negative sign on the R2 squared. If R2 gets large enough, it can kind of swamp R1 squared and C squared and make A go negative. Now, the other extreme is if C1 gets very large, then the intersection points can be driven out here past where C, this length C is. C will always be positive. Why? Because we're doing the coordinate rotate of the circles in order to bring the center of C2 always out to the positive X double prime axis. So C is guaranteed to be positive, but not A and B. And what'll happen if the intersection points are out here is that A will dominate, this A will dominate the equation here. And so when you take C minus A, you'll get a negative for B. So in other words, we could have the coordinate of the intersection points out here, and then the complement or the remainder from C, which is B, will be a negative value, bringing it back to here. So just want to point this out as one of the subtleties. There's nothing in this algebra that rules out having intersection points anywhere from here all the way over to here. And so you don't have to do anything here to condition this to work. Just understand that A and B can both, one of them can be negative, one positive, or the other one negative and the other one positive, but they still have to add up to a positive number C. Okay, so with that, it's time now to turn you loose to get on the general case, intersection of two circles, work yourself through your sketch to this special case, and then show how you're going to unwind your solution points in this condition space back transform to the original coordinates. Well, here we are in testing, intersection of two overlapping circles. Amazing. Okay, so we're able to solve all these cases, and I wonder if you noticed the same way I did that in order to get the height of the intersection point in the doubly transformed coordinate system, H, you could use a right triangle solver. And in fact, if you look at the output, the degeneracy output, it works beautifully to catch all your cases of degeneracy, which are both externally disjoint circles and internally disjoint. So that really simplifies catching all the degeneracy conditions just using that right triangle solver. That thing is turning out to be quite valuable. So again, thank you to Pythagoras for the theory behind the right triangle solver. Anyway, if you've got this working, you should feel a big sense of accomplishment at this point. As I said earlier, very few people can solve this. We're going to have some fun with this now going forward. There's a lot of interesting problems that solving this will open the door to for us. Don't forget to modularize. And there it is. There's our module encapsulating everything we just did. Well, that's my approach. Let's take a look at another approach. Again, for the third time, we'll welcome back Tour Guide A. He's taken a different strategy with this intersection of two circles problem. Let's take a look.
Hey everyone, I'm back for our third and final intersection algorithm. Let's jump into it. So in this video, we're going to be finding the intersection of two circles. In the diagram, you'll see that we have two circles, CR1 in blue and CR2 in red, and their intersection points I1 and I2 in yellow. Let's look at the attributes for CIR1. Now we first have the center position, C1, and the radius length, R1. Note that we have the same information about CIR2. Okay, so what we're going to do is we're going to find the position of I1 and I2 relative to C1. Now, the way we're going to do this is we're going to choose two directions, and we're going to see how long do we have to travel, what is the distance that we have to travel in each of the directions to get from C1 to I1 and C1 to I2. So the first of these directions is dir12, which is the direction of C2 relative to C1. Next, we rotate that direction 90 degrees counterclockwise to get dir_perp. Now we're going to call the direction that we have to move, or the distance that we have to move along dir12 A, and we're going to call the distance that we have to move along dir_perp D. Now, this means that I1 is going to be equal to C1 plus A times dir12 plus D times dir_perp. And notice that our problem is actually reflectionally symmetric over the line segment from C1 to C2. So that means if we reflect I1 over C1, C2, we'll get I2. And so that means that I2 is equal to C1 plus A times dir12 minus D times dir_perp. So our next step is solving for A and D. So first we're going to start by solving for A. Now, one quantity that'll help us solve for A is the distance from C1 to C2, which we'll be calling S. Now, remember that our problem is reflectionally symmetric. It has reflectional symmetry over the line segment C1, C2. So that means that for right now, we can just focus on finding I1, and then we can easily find I2 once we found I1. So we'll just get rid of that part right there. Okay. And now, remember that the distance from C1 to I1, the total distance, is R1, since I1 is a point on the circle CIR1. Similarly, the distance from C2 to I1 is also is R2. And now that we have all these quantities, what we can finally do is put them all into a separate diagram. So we can draw out the triangle C1, C2, I1, which we've done here. And by the Pythagorean theorem, remember that the line segment from I1 to this white point is perpendicular to C1, C2. And so that means that R1 squared is equal to D squared plus A squared, and similarly R2 squared is equal to D squared plus the quantity S minus A whole squared. Now, you can do the algebra on your own here, but when you simplify this, you should get A equals R1 squared minus R2 squared plus S squared, all divided by 2S. And based on the fact that the line segment of length D is perpendicular to the line segment of length A, and that line segment is one side of a right triangle, with the other sides being on R1 and A respectively. So now we can use the right triangle solver module on R1 and A to find D. Alright, now we're just going to put everything back together. So here's the overview of our algorithm from before. Now adding in the new information we have, here is our whole algorithm finally completed. Yay! Okay, so the one case that our algorithm does not cover is that of concentric circle. Now I'm going to ask that you pause here and figure out why this is. Okay, time to reveal the answer. Well, in this case of concentric circles, the distance between the centers of these two circles is simply 0. And unfortunately, that means that in our equation for A, we have division by 0. So what we have to do is weed out this case of concentric circles as one of the degeneracy cases. So why is this just one of the degeneracy cases? Well, there are indeed other degeneracy cases for this problem, but those ones are caught by our algorithm. So to understand why this is, we're going to have to look at a graph of A as a function of S, which we'll do right now. So here's our graph for A of S. Now note that for the rest of this video, we will assume that R1 is greater than R2, but this algorithm works for any R1 and R2. So they just need to be positive numbers and the circles need to be not concentric and our algorithm will work. Now, okay, the minimum of this graph is where S squared is equal to R1 squared minus R2 squared, which you can verify algebraically if you'd like. Now, to the left of this minimum, A is decreasing, but to the right of this minimum is increasing. Now, this might seem a little trivial, but along with the second fact, it's really going to help us see algebraically why our algorithm works for all cases except concentric circles. Our second fact is that when A is less than R1, SIR1 and SIR2 intersect at 2 points. When A is equal to R1, the two circles intersect at 1 point, and when A is greater than R1, the circles don't intersect. Now, A of S is equal to R1 for either S is equal to R1 minus R2 or S is equal to R1 plus R2, which you can verify yourself using the A of S expression above. Now, we have 6 cases. In the first 3, A is decreasing, and S is either less than R1 minus R2, equal to R1 minus R2, or greater than R1 minus R2. And in the second 3 cases, A is increasing and S is either less than, equal to, or greater than R1 plus R2. Now, over the next couple of slides, we're going to look at 2 things. 1, geometrically, what do these cases look like? And 2, why does our algorithm return the correct number and position of the intersection points in all of these cases? Okay, so the way we're going to go through these 6 cases is we're going to alternate one case where A is increasing, then one case where A is decreasing, and so on. And we're going to start with the cases that have 2 points of intersection, then 1 point, and then go to 0 points. So we're going to start with this case where A is increasing and S is less than R1 plus R2. Well, you might recognize this diagram. It looks very similar to the diagram we had a couple slides ago when we were constructing our algorithm. And that's because when we were constructing our algorithm, we constructed it using this case. So what we can do now is to substitute in the inequality, S is less than R1 plus R2, into our expression for A. Now, that's what we get, this inequality. And if you simplify it, which I highly recommend that you pause the video and do, you'll get A is less than R1. And what that means is that you'll see that the next line, D is equal to right triangle solver of R1 and A, is starred. And that's because that line determines the number of outputs that our algorithm produces. So in this case, since R1 is greater than A, we have that D is a positive number. And so D times dirperp is distinct from minus D times dirperp. And so I1 and I2 are 2 distinct points. Now, one last key feature to notice is that the center of this red circle is outside of the first circle. So you'll see that this is a big difference between the cases where A is increasing and where A is decreasing. So moving on, when A is decreasing and S is greater than R1 minus R2, you'll see that we have the exact same finding, meaning that A is less than R1. I'll omit the algebraic details for the sake of time, but that means that I1 and I2 are distinct once again. You'll notice here that the center of the red circle is now inside the blue circle. And you'll see that when A is increasing, the red circle center is outside of the blue circle, but when A is decreasing, well, now the red circle center is inside the blue circle. You might wonder, what happens if the red circle center is exactly on the blue circle center? Well, this means that in this case, there's still 2 points of intersection. You can kind of think about it visually. If the center of one circle is on the edge of another, then those two circles should have 2 intersection points unless one of the circles has a radius of 0. So hopefully that makes sense as to why all of these cases, which are defined using different inequalities with the quantity A, give us a lot of information about the relative geometric positions of the two circles. Next, when A is increasing and S is equal to R1 plus R2, we find that A is equal to R1, so that means D is equal to 0, and we have one solution. Similarly, when A is decreasing and S is equal to R1 minus R2, we can once again find that there is just one solution. Now, when A is increasing and S is greater than R1 plus R2, we find that A is greater than R1. So the right triangle solver module returns degeneracy. Thus, we have no solution as well as our second degeneracy condition. Lastly, when A is decreasing and S is less than R1 minus R2, we once again find that there is no solution and degeneracy is reported by this right triangle solver module. So that means that our second degeneracy condition, which is our final degeneracy condition, is just whether this right triangle solver is flagging degeneracy or not. And so that means our algorithm works in all cases, except when the circles were concentric. Alright, so that concludes our mini-series on 2D intersection algorithms. So, between what I've shown you and what tour guide F has shown you, you have two approaches to solving these sorts of problems. First of all, you have the geometric approach, which we just talked about. But you also have the transformational approach, which tour guide F showed you previously. Now, between these two approaches, you can use them in conjunction to kind of work through a lot more difficult problems, which, that could be in 2D or maybe even in 3D. So, best of luck with your future algorithm solving. See you.
Once I've got more familiar with the general strategy that Tour Guide A has brought to these intersection problems, things really started to gel for me, and after looking at his solution to intersection of two circles, I picked it up where he left off and took it a step further and can show you now a way to take this issue of where the critical point, or what we call the chordal point, is located. That is the key subproblem in solving this. And what I'll show you next is how you can reduce it to a simple formula, which is a linear combination of the two circle centers using the two radii. Here it goes. All right, so let's go back to the special case that was developed for intersection points of two circles in this specific configuration. Now we're going to work ourselves out of the need for the transforms that bring it into this configuration. But what we did find out was that A is equal to this quantity, A being the distance from the center of circle 1 out to this point. Here we're going to call this point P. This is the chordal point we're interested in calculating. Okay, it identifies where this chord that goes through the two intersection points will be located. And what we want to do is tie this back into Challenge 10, the discussion of linear combination, and the special case I illustrated where you can find a point interpolating along a line segment. If you know the fraction of the way the point is going from this endpoint 1 to endpoint 2, looks like it would be about 0.4 in this case, then all you have to do to calculate it is to form this linear combination. This would be 0.4 and this would be 0.6. Okay, so we can get the fraction of the way along that line segment. It's essentially just A divided by C will give us the fraction. And so we have A up here. All we have to do to get F is to take the right side here and divide it by C, which essentially will just put another factor of C in the denominator. And I'm going to rewrite this. I've got a C squared divided by 2C squared. I'm going to write that part as the constant 1/2. And that will leave over here just that difference divided by 2C squared. So there's our fraction that we can use to calculate the linear combination we're interested in. And if we want to splay this all out in its wonder, we can see now how we would form this linear combination. And so, yeah, this is F, the coefficient multiplying circle 2's center, and this is the complement coefficient 1 minus F over here, multiplying the center of circle 1. And it all looks very neat and symmetrical. And that's something that's going to pay off if you want to try to remember how this works in the future. It's got a nice pattern to it. So here's what that solution, the linear combination solution, looks like. So you've got your distance C between the centers. Here's your squares of R1 and R2 and C squared. You combine them. You come up with a value for F, the fraction of the way along that intercircle line segment. 1 minus F. You set up your linear combination, 1 minus F times C1, F times C2, and then the final step, we have to get the intersection point. So we'll generate the axis line. We can actually now go and look at this over on the other window. So I'll turn that on. So here's our axis line. And then what we do is we calculate the point P. There's our magic point P right there. And then finally, we'll generate a perpendicular to the axis line. It's like so. And then you can take the intersection of that line with either circle, and that will give you the two intersection points. And we'll use the degeneracy output of that intersection of line and circle to know when we've lost our solution to intersection of the two circles. So what you've got here is kind of a collaboration, an amalgamation of two different people working this problem, and the result is a very svelte, compact formula for computing the location of that critical point, the chordal point P, you just involving a formula which is a linear combination where we have just used the two radii and the separation spacing between the two centers. What I like about it is I'm looking ahead to 3D, thinking about intersection of two overlapping spheres, and that would be a circle 3D. And it seems like this approach I just showed is going to map exactly onto solving for that point, that same point in 3D, which would be the center of the intersection circle. So, this is great. Pack this away. I believe this is going to be very useful in the future. All I can say is, wow, this is really great. You're doing fantastic with this geometry, and you're going places that few have gone to, and you'll be amazed where this can take you in terms of even further. And especially when we get to 3D, you'll be quite impressed with what you solve today is going to do helping you in 3D. But we're jumping ahead of ourselves. So what we're going to do next is tackle a problem that you really need this intersection algorithm to solve, and that's going to be, given a circle and a point external to the circle, solve for the two tangent line segments that run from the external point and just glance the circle's exterior rim. And we'll see you at the starting line.